Okay, perfect. Thank you. And we are good to go. So tell us a little bit about yourself.
Hi, I'm Data. Welcome to Intro to Binary Exploitation. If you guys had attended TorHack last year, well, maybe I should say in 2019, I did the presentation on reverse engineering. So if you'd like to know about me for some absurd reason, then I am considered an expert in the fields of cybersecurity and physical security. So on the cyber side of the house, I do primarily binary analysis, exploitation, reverse engineering, and a little bit of pen testing. A lot more of the first two, at least in recent years. Additionally, on the physical security side, a lot of you may know me from a lot of LA cyber events where I teach the lockpicking villages or host lockpicking workshops. So I'm considered an expert on lockpicking, safecracking, and in general, non-destructive entry. If you've been to DEF CON, you've probably seen me at the Lockpicking Village or the Tamper Evident Village, where we run a lot of different contests and challenges and whatnot. So I am a big fan of hands-on learning and kind of doing cooperatively and collaboratively. So like Mike said, if you have any questions, feel free to put them in the chat. I don't mind them kind of as we go. Frankly, we're probably going to go over time in that I will not finish what I want in the time limit. So make sure you get your questions in now. Don't save them for later. As far as me, I help run Layer 1, which is Los Angeles's biggest security conference coming up at the end of May. For this year, we're virtual, I think for kind of self-evident reasons. So check out layer1.org. I'll talk a little bit more about it in a sec. But additionally, if you have heard of hackerspaces in the LA area, I am one of the founders of Nullspace Labs. Nullspace is, I would say, probably the largest hackerspace, at least in terms of active members and folks actively interested in doing security and kind of hacking related stuff, as opposed to more maker spaces or co-working spaces. So we're closed for COVID, but we hope to open back up in June or July. So check out Nullspace Labs either on Meetup or just Google Nullspace Labs. I'm sure you'll find us. As far as Layer 1, you should definitely come to Layer 1 if you liked the content you guys saw here today, both in my talk and all the other talks you've been to, as well as the hackathons. Layer 1 is known for being super hands-on, so a virtual event is a little kind of awkward fit for us, but we're doing our best to make sure there's a lot of contests and events and ways to both learn and network and meet people and do cool things is kind of our motto. So we'll be on Discord and Twitch, so check us out. I'll put the link to Discord in the chat at the end, so you don't gotta frantically rush to copy this down. So for the actual topic, what is binary exploitation? So you might have heard the term before, but just so that everybody's kind of on the same page, it refers to finding and or exploiting vulnerabilities in binary applications. So when we say binary, typically we mean something that is executable. And the primary goal here is to corrupt memory on the target system. So whether it's a server or a client or a phone or whatever, the general goal is to corrupt memory to hijack the program to do things it wasn't programmed to do. So that might not make sense logically, like how do you get it to do things that it wasn't programmed to do? And that's kind of the focus of this talk, is to get you started in this world. So obviously you're not going to learn everything there is to learn about this, massive topic in 45 minutes or 90 minutes, whatever we have here. But hopefully this gives you some good starting points for understanding, like, frames of reference for how things work and why they work, and give you some follow-up Googles to do to figure out what else you want to learn more about. So some of the words you might have heard before that are relevant to kind of what we're going to talk about today are things like buffer overflows, stack overflows, heap overflows, integer overflows, integer underflows, logical bugs, order of operations bugs, format string bugs, and or vulnerabilities. So this is all kind of part of a generic class of bug in software that is typically called memory corruption. And our goal here is to go from just normal use of a program, whether it's at a keyboard or on a web page or over a network socket or whatever, to being able to corrupt that program to do whatever we want it to do. So why does this matter, right? Uh, Kind of the long and short of this is that everything on your computer is on some level an executable, right? Either it's directly executable or it's given to something that is executable to be processed and to do whatever it has to do. So the question you should ask yourself, well, if executables have vulnerabilities and those can be exploited and everything's an executable, can everything be exploited? And when I mean everything, I really mean everything. So some examples are, I guess there's like a perception, at least for a lot of folks I meet, that some stuff is not important, right? So imagine like the Zoom software you're on right now, or most of you probably have Discord installed, or Hoova, right? Some app you had installed. So those are all executables, right? The browser you're running, potentially to access Zoom, is obviously an executable. All the network services your system's running. If you're running a server or something on the cloud, right, you're using web servers or some form of service running over the network. Also, your operating system is running lots of executable code, some of which is local and some of which is offered to the network or some other peripherals. And then there's some stuff that you might not think, like what about the piece of software that's rendering all of the pictures and text on your screen right now? Like in your Zoom chat over here, what about the thing that's actually converting the data to present the messages that people are saying, which includes their names and their message and any number of other things, right? So are those vulnerable? Because at the end of the day, they are executable code, right? And if you ask kind of a room full of people like, oh, I'm gonna hack your font renderer, right? They might kind of laugh it off and say that's not real, right? But the end result is that everything is vulnerable. Everything, no matter how innocuous you might think it is, or how small or how unimportant, everything can be vulnerable. And the goal of binary exploitation is to identify those vulnerabilities and then potentially exploit them. So we talked a little bit about font rendering, right, which seems pretty innocuous. So there are historically quite a lot of these. As it turns out, putting things on your screen is complicated, right? Think of all the formats in which we have to get that data, whether it's different languages, different literal like representations in terms of the font it uses. So historically, there's a lot of these vulnerabilities, and some of them are in your operating system. Some of them are in this example, Adobe, so in PDFs effectively. And you might go, well, data, you're old. These vulnerabilities are old. This is not real. This is not current. Well, I understand that these say 2015 here. So I put in one from 2020. So July 2020, we are still finding vulnerabilities in fonts, which in this one is at the operating system level, which means it applies to quite a lot of things. And also you note there, it says remote code execution, which means that you don't need to have local access to somebody to do this. And if you're interested in learning more, there's the CVE number. But kind of the point I'm trying to get across here is that this is not old or outdated or something you shouldn't care about, right? Every piece of software, from a security standpoint, you should ask yourself, should I run this? What are the risks of running this? And what happens if it gets compromised, and all that kind of chain of thought, right? So hopefully you're all very scared now. That was the plan. But as far as work and who does this, right? So there's kind of this generic class of security researchers. So folks that go out and look for vulnerabilities and bugs for the fun of it, often working for large organizations. So some examples of this would be like Rapid7 and IOActive and Project Zero, who specialize in operating system and browser bugs. There's also exploit development. So folks that are looking to actively hack other people, right? You have to find the bug and then you have to weaponize it. And there's a pretty direct relationship there, obviously, between finding it and using it. Additionally, there's a lot of reverse engineering that goes into this. So typically reverse engineering is how you find the bugs, and then exploit development is how you use the bugs to exploit a target. And whether it's for good or bad, a lot of these are sold privately on kind of black market exploit type stuff. You could say dark web or whatever you like. But on the kind of more positive side of this, a lot of this is done for bug bounties, right? So Historically, there was no monetary incentive to do this publicly, but now there is, right? You become part of HackerOne or a specific company's bug bounty, like the Google Chrome bug bounty or the Facebook bug bounty or whatever. And you find bugs, you exploit them to prove that this is a real thing, and then you provide all this to the companies, and then you get paid some amount of money. And then additionally, there's pen testing. So pen testing technically uses binary exploitation, but I wouldn't consider them a field that quote unquote does binary exploitation. So what I mean by this is they are using kind of completed exploits to penetrate systems, but they're not developing or identifying them before other people, if that makes sense. So pen testing uses this, but it's not the group that's generating more and more of it for everybody else. All right, so kind of the format for today, as best we can, is that I want to do kind of a collaborative capture the flag with you guys, at least a couple problems from it, however many we get through. And we're going to work exclusively on the binary exploitation category. So if you've never done a CTF before, CTF stands for capture the flag. And the one sentence description is that you're given a problem and you have to figure out the password that solves that problem, also known as the flag. So problems come in a variety of formats. They can be different categories. So there's exploitation, there's web exploitation, there's reverse engineering, forensics, crypto, kind of, et cetera. There's a lot of variety here. And you don't really know what the problem is until you open it. So some are go to this website and figure it out. Some are look at this source code and figure it out. Some are look at this image or this forensic snapshot of a file system. But the end goal is that you have to find the flag, which is the password that gives you the points. And then once you get the points, you trash talk all your friends and tell them how smart you are and so on. In a lot of cases, figuring out what the problem is, like how do you start solving it, is a big part of the problem. And I think for me, at least, it's also part of the fun, right? You don't know going into it necessarily what your process should be. And I think from a kind of learning and student standpoint, this develops muscles that you can't develop anywhere else, right? You develop this like hacker flexibility that lets you kind of approach a problem in an open-minded way and not worry about, I know how to solve it with this or this or this kind of thing. You have to kind of be a little more fluid and figure it out. And I think these are good muscles to exercise if you are interested in becoming a pen tester or an exploit dev, or even somebody that's doing incident response or DFIR. I think these are good muscles to develop so that you're not just approaching the same problems the same way, which I think limits your ability to solve harder and harder problems. So the specific CTF we're going to do today is Pico CTF 2019. So if you'd like to follow along, go to that link or Google Pico CTF 2019 and make an account real quick. Should take a minute or two. We're going to obviously focus on the binary exploitation category, but I really strongly recommend that you try other categories later, and try other CTFs later and whatnot. To, at least for me, starting out, I didn't know kind of what I wanted to do. I didn't know what kind of cyber I wanted to grow up to be, if that makes sense. So for some of you, it'll be DFIR. For some of you, it'll be binary exploitation. For some of you, it'll be cryptology, cryptanalysis, or whatever it might be. So I think CTFs are a good way to figure out what you like, even if you don't end up going into like a security focused job. So maybe this will teach you, I really like databases, or I really like programming, or whatever. And that'll kind of help guide you for things that you find naturally interesting.
Okay, so I just dropped the CTF link. So it's like a hyperlink in the chat for all the attendees if they'd like to click it and follow along. It's right there.
Thanks, Mike.
Yeah, no worries. Thank you.
Okay, so if you've never done a CTF problem before, they all work a little bit differently. Pico CTF is a Jeopardy style CTF where you basically have a big, what looks like a Jeopardy board of problems, and they all have categories, and you pick which one you want. In some cases, solving one lets you unlock the next one of that difficulty or that category of in difficulty order. Some just have them all open from the get-go. It really depends. So once you guys have made your account, you should be logged in. If I can find the page, should be logged in something like this. And also note, you might notice that there is a Pico 2021 CTF that's also up. We're not doing that because it just came out like 3 weeks ago. This class was developed kind of before that existed. So you're welcome. You're encouraged to try it, but that's not what we're going to look at today. So once you're logged in, you should have a tab that says challenge problems. You'll also notice that there's game and shell. Game is there's like a web game built into the CTF, so you can look at problems and do certain challenges specifically in the game. Again, outside of our scope. So if you're interested in that, I encourage it, but not today. There's also a web shell, which if you don't want to SSH into the CTF servers to work on problems, then you can use the web shell. Speaking of which, I don't think.
Sorry, what is the classroom name?
You don't need to worry about the classroom.
Oh, okay.
You could just play as a individual. I just have like teaching accounts. So like if I do an in-person event, I can set up a classroom, but you guys don't need to worry about that for today. Oops, ignore the man behind the curtain. Let's see.
Okay, and then don't join a team, correct? Play as an individual?
Yes, that is correct.
Perfect, okay. So if you haven't already, register. You will have to validate your account through an email. So don't put in an email, put in your email. Once you've validated, then click the link and it'll ask you for a team name. Just put play as an individual.
Okay. So I am going to use SSH, honestly, because if I use the web version, I'll push Control W and close the tab all the time. It's a terminal hotkey that I am not capable of not using. But for simplicity, you guys can use the web version. If you use the SSH version, you basically just SSH into the URL that's presented on the shell page. The first time you log in, it'll make your shell account. And then the second time you log in, it will prompt you for a password. And you can actually log in. Giovanni, there should be a US option. And honestly, it doesn't matter what country you pick, as far as I know.
This is very cool. I like this Unity game.
Yeah, the game is really neat. It's just it's right. It's not binary exploitation for today, but it's fun to play with for next time. Okay, so once you guys are logged in, you should have a click challenge problems up at the top center, and you should be presented with a long list of challenges. You'll see on the left, there's all the categories listed. So we're going to click only binary exploitation just to simplify our view here. So you'll see at the start, we only have 3 binary exploitation problems listed, right? And there's definitely a lot more than this. But the idea is that you solve easier ones to unlock harder ones. And easier ones have lower point values, harder ones have higher point values, kind of logically, right? So the first one we're going to do is called practice run 1. And if you read the description, it says you're going to need to know how to run programs if you're going to get out of here. Navigate to this path, and this path will be different for all of you. So don't try and copy it off mine, copy it off yours individually. Navigate to this path on the shell server and run this program to receive a flag. So what you'll find in a lot of CTFs is that they have kind of like a hello world problem just to get you familiar with how to submit a flag and the format of the flag. So like the literal text of the flag is often specific to a given CTF so that you know how to recognize it when you get one in harder problems, I guess is kind of the short answer there. So we are going to do practice run 1. We're going to go to the directory and we are going to execute the executable there. So I think for any of you who have done Linux before, this should be pretty easy. And frankly, I'm going to gloss over it because if you don't know Linux, some of this is going to be hard anyways. Okay, so I'm a CD there, I'm a ls, see what's there. See that this is an executable. If you look at the, your Linux class permissions hopefully taught you this, but it is executable. And when we run it, we get our flag. So again, this is not a real problem, right? This is just kind of an intro problem to get you familiar with either the shell server or the flag format or submitting flags or whatever, right? So just go to that directory, execute the binary there called run_this, and then that'll give you your flag. Copy your flag from your terminal or your web terminal or whatever it might be. And then come back here, put it in, click submit. And you'll see at the top right, it'll tell you if you got it right or not. You'll also see it marks it solved and hides it. You could also choose solved, unsolved for more filtering over here. I'm just going to let these stay shown on my side. Also note that if you open up practice run one, that's hard, to show kind of the thing, you'll see that there's a solve tab here, which is what we were reading. There's a hints tab here. So Pico is meant to be kind of like a helpful instructional CTF. So most CTFs don't really offer hints, or they're very limited that they will only offer hints if something's been unsolved by everybody for a long time. But Pico, I think, has hints on every single problem, and it doesn't cost you anything. So in a competitive CTF, it might cost you points to look at the hints or something like that. But in Pico, there's no penalty for it. So the hint here is pretty basic, right? Because the problem is pretty basic, but it says, how do you execute a program in a command line? So kind of the idea for these is they're trying to point you in the right direction. So if you Google like, Linux execute command line, you probably find instructions on how to do this if you didn't already know it. So I'm not going to click the hints for any of these in the interest of time, but I encourage you to do so as a learning tool. Like, don't feel like you have to solve it without the hint. Definitely try to solve it without the hint, but don't feel bad if you have to click it. Okay, so hopefully you guys solved that and got your first CTF problem solved. Now we're going to talk a little bit. So kind of what I want to get across here is kind of the overall process for doing binary exploitation. And there's obviously a lot of bits and pieces. So some stuff we're going to gloss over, some stuff we're going to deep dive, and hopefully we kind of fit it all in time. But I think the first part is like, how are executables made, right? And most of you would say, well, I give it to the compiler and the compiler spits out the executable from my source code, and that's that, right? The real answer is a little more complicated, right? So we obviously have source code of some programming language that is fed to a compiler. The compiler then generates assembly code. So the distinction here is that source code is typically not operating system or processor dependent, but the assembly is. So it's translating for the system you're compiling it on, or for the system you're compiling it for, into the appropriate assembly code for the actual processing chip on the systems that you want this to be executed on. The assembly code is like a human readable format, so you can think of it as like source code, but in assembly for the given processor. And that is fed into an assembler, and the assembler translates the assembly code into binary, also called an object file or an assembled format. A lot of different names for this, yeah. And then in most cases, you have what's called library code or dynamic code. So if you've programmed in C or Python or any number of other languages, you've probably done something like import or include to get other libraries code into your program, right? So in C, this would be things like printf, and any number of other standard library functions. In Python, this might be like import XML or import requests, or import whatever, right, is library code that's not included by default in your program. In most modern systems, we do this dynamically. So we mark that our program needs such and such library of such and such version. And when it's executed, then we ask the running system, hey, do you have this library? Do you have this code for me? And it's dynamically included into your running process. The purpose of this is that it makes your executable smaller, so you don't have to include all that code. But the downside is it's a little bit slower, right? Because we have to do that request when you run your executable. So the piece here, the linker that takes your assembled binary file, what it's doing is putting in placeholders for all the places you have library code to say, when this is executed, these placeholders need to be filled in, basically. And that's kind of the gist of it. And out from all this process pops our executable, which is in a variety of formats depending on your operating system. I will freeze frame this here so that if you watch the video later, you can read this part. This is kind of the more complicated explanation of how your executable goes from a file on your disk to a process. But I'm a little concerned that we don't have time to go through every step. So freeze frame. Cool. So if you watch the video afterwards, you can read more about this. And for every topic here that you're not sure on, I encourage you to go out and learn more, because I'm a dummy. Anybody who spent more than 5 minutes with me knows that I don't know what I'm talking about. So you should not trust my word. You should go do the research for yourself and validate what I'm saying is either true or untrue. But the end result of all this is that when you push enter to run that run this command to get our first flag, what happens is the operating system is reading that file off of the disk. It's then parsing all of its different pieces to say, this is an executable file, this is what kind of executable it is. And within the executable, there's a bunch of things, most notably our actual code, our assembled machine code is in that executable. And the header and data within the executable say where to put that in memory, and what we're going to call virtual memory, which we'll explain in a minute. And effectively what this has is an address for where to put it and how much to copy. And real executables are a little more complicated, and they have lots of different chunks of code to put in lots of different places. But this is kind of the high level view, is that our on disk executable data is copied into virtual memory and thus becomes part of a process on the operating system. So there's three things that are required in your executable that have to be there no matter what. So these are kind of the full explicit definitions, but basically your executable has to say how much data and from where in the executable file you're copying it to go to virtual memory. And then to put it in virtual memory, it needs a place to put it, so an address where that should be copied to. And then additionally, you need an address where to start executing from. So in your big block of executable data, it's extremely rare that you're starting at byte 1, instruction 1. More realistically, it's somewhere in the middle. So that place, wherever you're going to start from, has to be included in your executable. And these cannot be invalid, right? Otherwise, the operating system's ability to turn your executable into a running process doesn't work, right? It needs to have those three things at a minimum valid and available to the OS to be able to copy everything and get it started properly. Now you can obfuscate past this point, obviously, by making your code very complicated or do funny things or encrypt it and then decrypt it in memory and blah, blah, blah. But at a base level, these three things have to exist and be true. Okay, so what is a process, right? All of you use computers. All of you are familiar with the concept of I have a process. So what does that mean? So effectively, a process is some amount of data in the operating system for logistics, and then a big block of memory called virtual memory. So virtual memory is this idea that you have a, quote, transparent block of memory. So the process doesn't know whether it's in virtual memory or not virtual memory. And it's a protection mechanism for one process corrupting another, effectively. And anytime you need to like do something outside of your little house, you ask the operating system, aka the kernel, to do something for you. So at a high level, virtual memory looks something like this, and I'm sure you've seen it in your textbooks, but effectively it's a structured way of sorting all the pieces of data that a process needs. So they're referred to as segments. So your text segment has your actual assembled code of your program that was generated by the compiler and assembler and linker process. The stack and the heap are used for dynamic data that happens during execution. And then the data and BSS segments are used for what's called static data. So the kind of classic example here is that if you say like print and then in quotes, hello world, that hello world string is a static piece of data that in the majority of programming languages will never change or cannot change. So that is put in data because it is a static piece of data that is defined, as an example. And then up in the kind of here be dragons part of virtual memory is a place reserved for the operating system, aka the kernel, to kind of never be touched by the rest of what's called userland processes. And you're saying, well, this is 32-bit. How does it differ in 64-bit? It doesn't, other than the numbers are bigger. It's basically the only difference.
If you would like, we do have some questions here.
Okay. I don't see them in chat.
Yeah,
but I
they
believe you.
sorry, there's also a Q&A section on Hoover. So I can read them for you.
Yeah, by all means.
Perfect. So what is the purpose of binary exploitation?
To hack other computers.
Perfect. And then let's see, we got another one here. What would be some of the most vulnerable what would be some of the most vulnerable pieces of hardware to fall prey to binary exploitation?
Historically, it's anything that does data parsing. So like the initial thing that is accepting data from a user or over a network socket or something, those are historically the most vulnerable things because the idea of parsing arbitrary data is very complicated. It might sound simple, right? Like, oh, you just parse the data. But there's a lot of technical nuance into the formatting of data, the size of data, uh, having data adjacent to other data and all sorts of other kind of nuts and bolts, very low level concepts at the binary level. So historically, its parsers are very targeted, which is why something like Adobe Acrobat parses PDFs. This has a lot of vulnerabilities historically because it is a giant parser that displays something to the user, and it has, hundreds, if not thousands of features, which could be vulnerable to somebody making a malicious PDF.
Perfect, thank you. And then we'll do one more here and we'll save the rest for later. What is the difference between binary exploitation and reverse engineering?
So reverse engineering is, they're very related, right? So you use reverse engineering to help accomplish binary exploitation, but reverse engineering specifically refers to taking the executable, so the end product of the compilation process, and trying to figure out how the program works given the lack of source code, right? So by looking at the assembly and et cetera, we can figure out what the original code might have been, or at least functionally like an equivalent representation of what the original source code does. So I think for all of you, you can say, if I had the original source code, I could figure out what the program does, right? Like that's an easy logical leap for most of you. And then the next leap is to say, if I had the assembly, which was derived from the source code to make the executable, could I figure out what the program does on that level, right? And it's the same process as reading source code. You're just reading assembly source code as opposed to original C or Python or whatever source code.
Perfect, thank you. And then we'll save the last two for later.
Okay.
Thank you.
No worries. So the next bit is kind of comparing like, why do we need virtual memory? Like, because this has kind of a big impact for exploitation. So historically, we had what's called flat memory models. So all the processes existed in like literal memory. So imagine you have a 4 gig RAM chip. Process A gets this little slice and process B gets this little slice, and etc. But the problem here is if everything shares and is allowed to kind of touch everything else, then there's pretty rapid problems with any small bug. So imagine we have data as bad code. Now, I understand this is a fictitious scenario because I would never write bad code. I understand. We'll just have to turn our Imagineering on for now. But imagine I wrote really, really bad code, and my code affected something somewhere it shouldn't have. So in some other process's memory space. And that process needed that data that I overwrote to make decisions. So process A goes to look up its data to make decisions based on who to allow access to something, or where something should be sent, or any number of other things that can ruin your program, right? And process A decides to use that data that is now corrupted by data's bad code to write more data, and it keeps writing bad data and bad data. So typically any little problem in flat memory layouts results in like a full system crash, because you have this kind of butterfly effect of effectively all programs are doing is processing data and making choices based on what the data is. And if you corrupt that data, that leads to typically blue screens historically. So obviously blue screens still happen, and this is caused for a variety of reasons in modern computing, but at a base level, this is data gets corrupted, and then your program ceases to function properly and causes crashes or exceptions. Or in Linux, this would be a kernel panic. In Windows, this would be a blue screen. Any number of other kind of similar scenarios for embedded devices. So given the problems with the flat memory model, effectively what happens is we decided to create virtual memories. So every process gets their own little house, and in their house, they have basically the same worldview where they have their own text segment and their own data segment, and et cetera. But each process is only allowed access to its own virtual memory, so its own little house. It can make its house as messy as it wants, but if it explodes its own house, it doesn't affect everybody nearby, and it doesn't affect the kernel, and so on and so on, right? So this is kind of the reason for this. And this is why we say, quote unquote, it's transparent, because the process A doesn't know that it's isolated from process B at some level of context, right? Okay, so with that kind of small tidbit out of the way, let's talk a little bit about shellcode. So if you guys look at the description for handy shellcode, which is another binary exploitation problem, it says this program, and it gives you the binary as well as the source code at the end here. It says this program executes any shellcode that you give it. Can you spawn a shell and use that to read this file flag.txt? And then it gives you, again, the path to the problem on the server. And for those that joined late, your paths will be different than everybody else's. So don't worry about copying mine, just copy yours. You can pull up the source. If you want to look at it in the kind of reverse engineering view of the world, you can look at the executable purely. But we're going to look at the source in the interest of time and being beginner focused. But first, I'm going to go here on the server. So if I look here, I see that there's three files. There's flag.txt, there's vuln, which is the executable, and then there's the source code again. So effectively, they give you the source code here, so you can look at it on the shell if you'd like, but you can also download both of these. To actually get the flag, you'll have to execute it on the server, because the server has the flag.txt that you want. So you might say, well, there's the flag. Let's just look at it, right? Well, okay, let's try and look at it. Well, we get a permission denied. And the reason for that is that it's owned and only readable by this Hacksports user and this handy shellcode 2 group. And we are not that user and not part of that group. So if you're familiar with Linux, effectively this S right here means it is set GID. So when this program executes, the default in Linux is that you execute with your permissions of the user you're logged in as to prevent security problems. But the set GID, and there's an equivalent one for users called set UID. This permission allows you to, when you execute it, run as a different user. And you might say, well, isn't that a vulnerability? Well, kind of, but the majority of kind of system level programs on Linux, things that do like very critical functions are set UIDs or set GIDs. So some examples of this are sudo. Obviously, sudo lets you run as other users. So it has to have the ability to run as many different users, typically root privileges. Similarly, passwd, so the thing to change your password, has to have access to write that password to the system file that stores passwords, which is also root owned. So this happens a lot for some core things. But obviously any vulnerability we find in those lets us escalate our privileges to that user. So in this case, we have a pretty clear vulnerability in that the program or the problem tells us you get to execute whatever you want. So that's kind of interesting. So if we look at the source code, I'm assuming you guys either are looking at it on the terminal server or you downloaded it and opened it up in Notepad or something like that. But effectively, we see that this is obviously a C file. It's called .c, and the language looks like .c. We see that it really does just take our input and execute it. So makes a buffer, calls this function vuln. This function vuln will read input from us and then echo it back out to us just so that we can see it. And then it will do this long, complicated string of C, which basically means run that code as a function, run that input as a function. So we're directly translating user input into executable code. We're kind of cheating right now, but this is just kind of a stepping stone to get a little further. Okay. So I will leave that up. Go back over here. So it's pretty clear like what this wants us to do, right? It's going to take some input from us and then it's going to run it as if it was executable code. But how do we make that translation from things we are typing on the keyboard or data we are providing to this program to executable code? Because I think many of you know that executable code is not readable in that you can't just type it out with a keyboard easily. This code is known as shell code. So basically, this is the basis for a lot of exploitation in that we are exploiting some vulnerability that allows us to execute code, which we're going to call shell code. Historically called this because we give it code that makes a shell. So in Linux, we'd make a bash shell. In Windows, we might make a CMD shell. Technically, the code we give can do anything that we have permissions to do. So it can delete files, add a user, delete a user, anything we have permissions to do. But a shell is the most flexible because with a shell, we can now start typing our normal commands in to navigate the system we exploited and yada, yada. So kind of the key points here are that this is written in the assembly language of the target. So on the other end of this is a 32-bit Intel program. And if we want to verify that, we can run file on this and see that it is 32-bit. ELF is the executable format used by Linux, stands for executable and linking format. We also see that it's Intel, again, 32-bit, 8386 is the 32-bit Intel marker. And then a bunch of other data, which we're going to kind of ignore for now. But we see it's 32-bit Intel, and obviously we know we're on Linux already. So again, to reiterate, shellcode is assembly that is written for the target processor and often written for the operating system or specific software of the target. So Windows shellcode does not look the same as Linux shellcode, does not look the same as ARM shellcode or any number of other processors or operating systems. Okay, so how does shellcode work and kind of what are the nuances of this? So again, in assembly, we're writing code that does a task. In our case, we're going to make a shell. We can do this remotely. So there's this idea of remote code execution is the idea that we're doing it over a network socket or not sitting at a computer where the software is running. But we're not going to cover that today because frankly, it requires a lot more code and more time than we have. The other kind of key note here is that we inherit the permissions of the software we compromise. So any vulnerability takes the permissions of that process and allows you to work within that context. So if you compromise an admin process, you become an admin effectively. And this is why you're often told don't run things as administrator, least privileged processes and users and all that kind of stuff. Because if it gets exploited, it takes over those permissions. So how do we make shellcode? So this is shellcode. It's very exciting. It's really readable. So we can probably just end the class here and you guys are good to go, right? And I've also put 2 different versions of it that do basically the same thing. So it's fine. I understand you don't know what this means right now, but effectively what we're doing is translating the binary data of our code into a form that we can read and input over the command line. So for those of you that recognize this is just hexadecimal notation for kind of arbitrary bytes. Some of these have like normal keyboard representations, some of them don't. And the reason there's 2 versions is that because the assembly code in each of them is different, but they have the same end result. They do the same function. You'll see that there's some parts here that are the same. This like CD80 is a very common 32-bit Linux shellcode instruction that's very common. So I can read it like this, but I know you guys can't, and we're not going to worry about it too much about why it does what it does for now. But effectively, we're going to take our shellcode, we are going to feed it into the program as it's asking for, and then we are going to get a shell. Now, I put this paste bin here, and I will type it into the chat. Which I believe I did not typo. So you can go there to pull the shellcode strings that I listed. Effectively, all I'm doing to get those, if you can write it yourself, but you don't have to. But effectively, all I'm doing is I'm going to Google. I'm saying Linux 32-bit shellcode. And from here, there's quite a variety of these depending on this amount of input you can provide. Sometimes there will be a character restriction. So like imagine maybe the thing processing our input doesn't let us take 2F, right? So some versions of this will have these or not have these, and you can kind of filter on that. You can also generate shellcode if you get more advanced with some of the Metasploit tools like MSF Venom to generate shellcode that doesn't have specific bytes so that you can bypass filtering and other restrictions for exploitation. But effectively, this is just one of the shellcodes I have listed. And you can read the assembly up here if you're familiar with it. Typically, it's a good idea to disassemble this to make sure it matches what they're saying it does. Otherwise, you are potentially running something that you don't know what it's going to do when you push enter. So again, in all things, practice safety and security, especially when dealing with exploitation. So I'm going to assume that you guys went to Pastebin and pulled that. I will pull this one just for funsies. And I'm going to do exactly what is listed on the slide here. We're going to try this like this. And you might be wondering, why am I doing this cat? Why am I putting it in parentheses? So I'll show you both ways just so that you get an understanding of what is different about it. But you should have the full command in that paste bin, so you don't have to do what I'm doing. Okay, so those familiar with Linux will know that echo just prints something out. The -E option will let us print the actual binary instead of printing literal / literal x, literal 3, literal 1, etc. So like, for example, if we just do this, we'll see that it's not really readable, right? And it's not what we inputted, it's the translated binary version of it. So if we do this, and then we pipe it to vuln, so again, we're providing data over standard input, which is just piping something to the process. We already read the source code, so we know that doing this is how it wants the data as opposed to a command line argument or something like that. And then if we hit enter, we see that it says enter your shell code. It prints it back to us, just like we had seen in the source code. It says thanks, it's executing now, but I don't get a shell in that my permissions haven't changed. I'm still DG teaching 4. I didn't inherit the permissions of this. So effectively what's happening is that if you don't do this cat stuff in here, and it doesn't matter if you have spaces. So if you don't do this, you don't get a shell. And the reason for that is the act of piping data in like this causes the bash process that gets generated to say, I don't have any more input. I already consumed it all. Therefore, if I can't have input, nobody can run commands and I should close is kind of how the process is thought process. That's a mouthful. So again, if we do in parentheses with cat, the cat program will hold those input outputs open for us. And we see that instead of just kicking us back to a shell, suddenly we're at this kind of blank, mysterious line. And many of you may recognize this as a shell. It says, oh, okay, I'm still DG teaching 4, but if I look at my permissions, we see that now I'm running as the set group ID that this process had access to. So I've effectively elevated my permissions or changed my permissions to the vulnerable process. And I could do it. I'm effectively in a shell. It's ugly. Like we don't have a prompt. We can't do like up and other fancy shell stuff. But we have a shell, and we can start navigating the file system as though we were a user in that group. So as an example, we can read the flag file. So Mike, I can only assume there is at least one question so far.
Sorry about that. No, actually, we've got 2 right here. So, is binary exploitation related to hacking?
Binary exploitation historically is hacking. More modern definitions of hacking would include web exploitation, network exploitation, and other stuff that may or may not use binary exploitation, depending on how you want to define it. But I think at a base level, binary exploitation is hacking, or at least the classical definition of like hacking a system to do whatever you want with it.
Perfect. Just like the parsing you were saying, correct? With like PDFs?
Yes.
Awesome, awesome. And here's another one. This is the last one I've got. What computer language is most related to binary exploitation?
So question is, what computer language is most related? I would say on the not assembly side, C and C++ certainly are the most used languages. Typically, I think it goes outside of the scope of this class, but typically when you are doing reverse engineering, you're looking at either assembly or C. And if you're reading source for low-level languages, you're looking at C or C++ for most embedded devices. So if you're saying not assembly, then it's C or C++. If you're saying assembly, then it depends on what the actual target is, right? So if the target is running an Intel 32-bit processor, then it's Intel 32-bit assembly. If it's 64-bit, it's Intel 64-bit assembly, and so on, right? So again, we are writing exploits for our targets specifically, and how that kind of plays out depends on what you're targeting, who you're targeting, etc.
And so, and that's for like kind of like hacking hardware.
It's just no. So this is not hardware specific in the sense that we're not quote unquote hardware hacking. We are, to get the other side to understand what we're telling it to do, we have to speak its language, and its language is dependent on its operating system and its processor.
I see. Perfect. Thank you.
Okay. So hopefully you guys followed along and got this flag as well. I'm gonna just throw this in real quick to unlock some more. And again, your flag is gonna be slightly different than mine, so don't copy mine. Cool, we solved that one too. And you'll see as we're doing this, we're unlocking more and more problems related to binary exploitation. So the next one's called overflow 0. Then there's slippery shell code and so on. I think we have, what, 20 minutes left, Mike?
Yes, we do. So if you want, if you do have time left over, feel free to plug layer one conference more if you want to go into specifics.
20
I don't
minutes
mind
of
at all.
plugs. I got
Sorry.
you. 20 minutes of plugs, right?
You if you want, go for it. I'm giving you full reign here.
So Ed, I see your comments. I have a slide at the end that's some resources, but I'm gonna just wait until then to answer that. So as far as like some of you might be asking, those of you actually interested in kind of learning more about this, kind of what is assembly? How does it work? So kind of the most interesting part about assembly is that it's a mnemonic language. So this is not true of any other programming languages other than assembly. But effectively what this means is that there's a direct translation between the human readable assembly code and the binary representation. So you can both translate back and forth. So you could translate the human readable into the binary and the binary into the human readable. And unlike source code, there's really not a whole lot of information lost because there's no like names of variables and kind of other stuff at a high level, right? So some examples down here are some example Intel 32-bit instructions and their corresponding binary translation. So when the processor sees these bytes, let's say it's pointing to this spot to execute, it reads 31 D2. It knows that that is a XOR EDX instruction. And I guess if I know you don't know what that means, but I promise you the processor does. Okay. So kind of how these work is that these are all predefined by the processor manufacturers. So every bit of the instruction has a meaning typically. In Intel, instructions are variable length. That's not true of all processors and all assembly languages, but for Intel it is. I think obviously if you guys didn't know, Intel is probably the most popular in the top 3 of processors worldwide, with the only reason it's not number 1 now because of mobile phones use ARM and other kind of stuff. But yeah, it's a pretty direct translation and every bit has a meaning to assist the translation process. Okay, so if we look at our shellcode translated, it's this. Again, it's very readable. I know that you guys are just fully aware of what's going on and you can now hack everything without my help. But effectively, we're not going to be able to cover this in the time we have left, unfortunately, but effectively processors are 3 things. So what I want to get across here is you should not be scared of assembly language. If you want to do binary exploitation or most forms of reverse engineering, you will have to learn assembly. And it is not as hard as most people make it out to be. The trade-off is that assembly language instructions are very simple. They do one specific thing, which means that you need a lot of them to do complex tasks that would otherwise be a single function call or a single operator in higher level languages. So the way to think about assembly in a nutshell, to kind of translate for yourself how to go from assembly to how is it processing, is that all assembly languages are based on 3 core concepts. So number 1 is instructions. So whatever is being executed at a given time by the processor. There's also registers. So you can think of these as buckets where data can be processed and arithmetic and whatnot on the CPU itself. So think of it as like a little variable that you can reassign the value of and perform computations on and make decisions about on the processor itself. And then there's memory. So everything that's not in a register effectively exists in memory for the process. And again, this is every processor, every assembly language. There are some obviously differences, but in a nutshell, these are the 3 core concepts. So to reiterate, you have code stored in memory that can be translated to instructions based on our binary to human translation. The processor has a pointer that says I am executing here, and then it kind of goes sequentially down to the next instruction, unless told otherwise. Those instructions perform actions that affect registers, which are data stored in the CPU, or memory, which is some value stored at an address in our virtual memory, right? And that's effectively all that happens. Now, instructions typically execute sequentially, but every now and then you'll have one that says, instead of going to the next one, go somewhere else. So this is things like making decisions, like your typical if conditional in like C or Python or whatever. You say if such and such, do this, otherwise do this. This is a choice at the assembly level for what instruction to go to next, effectively. Okay. I am going to skip a couple of these in the interest of time, but we already talked about instructions are basically just a human readable thing. They have arguments. Some are memory addresses, some are literal values, some are addresses or register names, sorry. And instructions only do three things. They do arithmetic, which is computations or calculations. They do data retrieval or data storage. So typically you're putting data or taking data from memory or registers. And then they do control flow, so deciding where to execute next. And that's it, right? So it doesn't sound particularly complicated, but obviously there's a little more nuance than that. The other kind of key point here is that instructions coexist with data in memory. So our virtual memory contains both the literal data we want to work on, as well as the instructions and code we want to execute. The difference is that the portions of memory we want to execute from are marked as executable. So the processor kind of knows which one it should and should not execute, in that if you try and execute something that's non-executable, your process will crash effectively. Okay, we're going to skip what registers are, but I'll leave it here for a sec so you can pause it. And same for memory. I think memory is fairly straightforward. I explain it as, imagine you have Excel, but you only have one column. And so you have your address, like, row 0 is this value, row 1 is this value, etc. And that's effectively all memory is. So what most shellcode does, and what the shellcode we were looking at, what that does is run a C or system call function that executes a process, and we give it the name of that process in the form of a path on the file system. So in C, this is execve, and then we give it bin sh as a string. The nulls are for some optional arguments that we're not going to worry about. If you've done Python, this is effectively equivalent to doing os.system in Python. So it's simpler in Python to some extent, but effectively it's doing the same thing somewhere down the line as you go from Python to the C Python interpreter to the operating system to the assembly level, blah, blah, blah. Execve is what's called a system call. So we talked a little bit earlier about if you are doing things that interact with the rest of the system, you need to ask the kernel to do it. So effectively, this is a system call, and a lot of things are system calls, like opening a file is a system call, reading a file is a system call, opening a new process, as we're doing here, is a system call, changing permissions or changing the state of processes or the state of files, the permissions of files are often operating system calls. And a lot of these exist as functions in whatever programming language you're using, but they correlate back to the operating system specific thing or way to do it. So again, in Python, you might do open as a function call. That is eventually calling the open system call in Linux. And then when you want to read data from that file, it's using the read system call, and so on and so on. Okay, we're going to skip that. So what's kind of interesting is that one of the big changes between 32-bit assembly and Intel and 64-bit assembly is that system calls are very different. So if I give you one kind of tidbit going forward to help you understand the difference, is that system calls in 32-bit use what's called the stack. So that's the region of memory that we talked about, but we'll probably not have time to cover. And in 64-bit, you put all of your arguments for a system call in registers instead. So this is kind of the distinction, and something that might trip you up if you are used to one or the other. You're working on a problem or a work scenario that involves both. So just keep this in mind. This is by far the biggest difference between 32-bit and 64-bit Intel assembly. Okay, I know you're all like, Data, we didn't hack anything yet. What's going on? I understand. There's a lot of overlapping technology to worry about, right? So we're trying to distill 50+ years of computational and exploitation topics into 90 minutes or so. So I understand. So let's look at the next problem, and it'll probably be a homework assignment, but hopefully we'll give you enough to figure it out, right? So let's take a look over here. So our next problem is going to be overflow 0, right? And my favorite part about this one is it says this should be easy, right? So that's very motivational, right? It's probably not that hard. Overflow the correct buffer in this program and get a flag. And then they give you the path, they give you the source code. So that's interesting that they're saying just override a buffer. So let's look at, oh, by the way, if you are still in your shell over here, just type exit, just like if you're in a normal bash shell. And then that will kick you back to your real shell. In case I didn't mention that. So let's look at our overflow 0 source code. All right, so we're going to start in main just for simplicity. We see that it's opening a file called flag.txt. Now remember, this all happens on the challenge server, right? So if you run this locally, you're probably not going to have a flag.txt to work with. But on the server, it's running open a flag, and then it sets up a signal handler. So signals in Linux in 5 seconds are basically like, if your process does something it shouldn't, it typically generates a signal, which the operating system then handles to decide what to do. So an example is a crash. A SIG-SEG-V stands for segmentation fault. So if you crash it based on memory access, it generates a SIG-SEG-V, and then the operating system knows how to handle that if you set up the signal. There's others that are a little more commonplace to like pause execution or wait on input and blah, blah, blah. But I'm sure you can all Google Linux signals if you want to learn more. So what it's doing is it's setting up a segmentation fault handler with this function called SIG-SEG-V handler. So what does that do? So if we read that, we see that it prints the flag for us. So that's pretty interesting. So how do we generate a segmentation fault? So a segmentation fault occurs anytime you go out of bounds, right? So if you try and access a memory address that doesn't exist or that you don't have permission to ask or to access, then it creates a segmentation fault. If you try and write to a region of non-writable memory, it causes a segmentation fault. If you try and execute a non-executable part of memory, it generates a segmentation fault. So I guess our homework assignment here is, given this problem on the server, how do we generate an segmentation fault? And I would say, as your homework, look up strcopy and figure out the ways in which you can do this to kind of go forward with this. And from here, the problems build on kind of this set of ideas for how to go from just running a program to providing input in a variety of ways and exploiting it and getting to the point where you are feeding it a wide variety of input and custom shell code and so on. So I think these are really good problems to work on. Even though the first time you do it, you're going to beat your head against it for 6 hours, wondering why it's not working. It's going to be a lot of tears and pain, but it will all be worth it. So I'll leave that as homework for you to go forward. If you've already gotten past the part of being afraid of assembly and all that, I think you'll be fine. But unfortunately, we just don't have too much more time, and I did want to answer some questions. So feel free to ask questions. I think while Mike's sorting that out, I think good reading for doing more advanced exploitation once you get familiar with the basics. So I would Google, buffer overflows, stack overflows, heap overflows, all the stuff I presented earlier. Once you get past that, there's more modern advanced exploitation, which is non-executable stacks, ROP, ASLR, stack canaries, and so on. And there's lots of tutorials and lots of learning resources out there. Ed asks, is the solution to point to a valid block of memory? No, you want to cause a segmentation fault to get the program to give you the flag this time in this specific case. So you want it to crash. And there's a variety of ways you could do that, but one pretty simple way, if you look up what strcopy does and how it works. And the first thing on strcopy's man page is probably like, don't ever use this ever. So as far as some resources, so I think CTFs are the best way to learn a variety of skills. Obviously, there's books you can read if you Google, like you just go on Amazon, look up binary exploitation. There's Hacking the Art of Exploitation is probably the most common book. There's also Shell Coder's Handbook and a number of other ones. But I think the majority of data that's digestible does not come in book form, at least currently. I think if you want to get kind of more, again, reps at the gym, you want to go to ctftime.org. This shows all upcoming and past CTFs. And for past CTFs, users upload write-ups, which is basically a walkthrough of how they solve the problem. So you'll find this for, frankly, Pico CTF 2019 and 2021 as well. But I would encourage you to try it before you look at the answer, just to learn a little bit on your own and then add whatever the solution is if you can't figure it out to your repertoire. Some of the CTFs don't exist all the time, so I chose Pico because it's always available forever. But some CTFs only run for the weekend that they're alive, kind of like your hackathon that you guys are doing now. And then it goes away, right? Because people don't want to maintain this forever, right? Some of the infrastructure for these is pretty expensive and complicated to maintain. There's also what's called, we talked about Jeopardy CTFs, there's also attack defense CTFs. So these are ones where instead of given a problem, you have a whole network to take care of, and you have to defend your network while attacking other networks. So this is kind of a hybrid of pen testing and CTF and DFIR and or blue teaming. And so those are interesting. I think at the kind of academic level, this is like CCDC and Cyber Patriot and other stuff are basically this idea of attack defense, but there's obviously a lot more out there. So I've rambled enough. Hopefully we have time for some questions.
No, thank you so much. This was very educational. And this is coming from last year's Toro Hack 4.0. Big shout out to the previous organizers. They are attendees actually to this year's Toro Hack. I went to the hackathon. I got 1 point. I didn't know anything. So if you like Datagram's been saying, if don't feel bad, don't let this deter you. This is where you start, and I'm telling you, it's a chaotic but very fun journey. I'm sure you can probably say the same.
Yeah, I accidentally won some of the prizes from last time's Tour Hack because there was like 500 problems. So I solved all the problems in the exploitation category, thinking like somebody will solve like the other hundreds of problems related to the other topics. But I guess I didn't realize they were category-based prizes. So I won that, and I'm sorry for stealing your gift cards. I gave
Oh
them
no,
away if
no
it makes you
worries.
guys feel better.
It's great having that kind of competitive edge, and just like Leah said, Leah says I've cried at so many hackathons, but it's totally worth it, and I agree. It can be brutal, but it is so much fun. Last year, like I said, I made 1 point, but this year I ended up learning Feistel cipher, and I designed 256 questions for this year's hackathon at Toro Hack, and like I said, this was a year ago. So much fun, so much fun. But thank you so much, Datagram. This has been, you were great. You feel the whole time, and it went really well. I don't want you to think like you were saying before, like that it was too much, or you did really great. It was really great,
That's fine.
and thank you so much for doing this.
To answer Ed's question, which is a good question, what certs might help? There's really only one cert right now that covers this that's like widely available. It is, well, frankly, I don't know what they call it now because they just changed it, but it's the Offensive Security Certified Exploiter or Exploitation, OSCE. So OSCP is the pen testing one. OSCE is the exploitation one. And they just changed it and redid it. So I think they have a new name for it, but I frankly don't know what it is. CEH does not cover binary exploitation in the sense that you will not do any hands-on binary exploitation in CEH. You'll do a little bit of it in OSCP. There are some buffer overflow problems in the OSCP lab, but OSCE is really the only dedicated exploitation course that's like beginner focused. SANS has, I think it's called SANS 760, which is like advanced Windows exploitation or something like that. They don't offer it I don't think you could just go buy it like you can the other SANS courses. It's like an in-person, you gotta like ask to be a part of it kind of thing. But that is for more advanced exploitation. And I would say you probably want to be taking OSCE and potentially others before you take that.
All right, perfect. So that is all of our time. Again, Datagram, thank you so much for coming. Hope to have you next year. And yes, layer one. So let me actually I'll type out the link for.
I can paste it in so you don't have to
Okay, perfect. Yeah,
transcribe it.
paste it in. And I will spread that around because like I've been saying, you've been such a huge help to us. I would love everyone here. If you enjoyed Datagram here, this is a conference that he is running, and you know you'll learn so much from him.
Yeah, I appreciate it. Come to layer one, come to Null Space Labs. And if you guys have any questions, I'll be in the chat until, well, I guess you guys have closing ceremonies, so I'll be in the chat for a little bit, but I know a lot of you are going to migrate off to the other track for closing. But I'll be around if you need me, and you can always jump on the Discord and find me there.
Perfect. So I will actually I'll leave this up for a while for anyone who wants to copy down, maybe take a screenshot. And yes, like what was mentioned, at 4 p.m. we're gonna have our closing ceremony. So we will reveal winners of the photo contest, the Huva engagement leaderboards, the esports. The esports tournament might be finishing a little late, so hopefully we'll have a winner by then, and the hackathon. So keep an eye out for that. Again, closing ceremony is at 4 p.m. Thanks again, Datagram.
Sure. Thank you. Thanks, everybody.
Hello, everyone who's still here. So, again, keep an eye out. There will be closing ceremony at 4 p.m. So, in about 5, 6 minutes, and I will see you all there. So, I'm going to close this meeting. And thank you so much for attending. See you there.